Okay, in this video, I'll be quickly going through the 2024 past physics paper 2. Here we go. There's only like 8 questions, I think, so yeah, it should be pretty easy. Hopefully it's the same as, it's the same in the externals, but we'll have to see on Monday. Okay. Question 1. A coil of wire with 100 turns and a radius of 1.4 centimeters is placed perpendicular to a magnetic field of strength 0.51 T, so Teslas. The magnetic field strength is then changed to 0.03 Teslas in 0.02 seconds. Calculate the magnetic magnitude of electromotive force induced in the coil. So we're just after the magnitude, so we're using Faraday's law. Okay. So we have to use this formula. Just ignore the working out. Yeah. Okay. I'll draw like a line. This is my video that I'm currently uploading, So you'll probably see that video uploaded first. Okay, so we're going to use this formula. EMF equals negative n, which is the number of turns or the number of loops, multiplied by the rate of change of magnetic flux. Okay, so it's given that there's 100 turns, so n equals 100. Radius, so radius would be involved in the area. And then, okay. So let me just write this all down. So EMF, we're calculating EMF, n equals 100, r equals 0.014, because it was 1.4 centimeters. We're converting it to meters, so we're dividing by 100. It was placed perpendicular to a magnetic field of strength 0.51 Teslas. And then it changed. B was 0.51. That was initial. Final 0.03. T, the change in time, equals 0.02. It's perpendicular. Now, I am missing something in this formula that I wrote. If you look over here, as you can see, it's not great, because I'm uploading. We navigate over here. So magnetic flux equals BA cosine theta. I believe cosine theta in this case. I'll have to revise this, really make sure I'm correct, but cosine theta, obviously it's 0 in this case. Cosine theta is 0. But I think it's the angle of the, so we have the loop, right? So pretend this is 3-dimensional. So the normal of the loop of wire is this, and it's the angle that this makes with the magnetic field, I think. So since it's parallel, the normal is to the loop is parallel. This is 0 degrees, which cosine of 0 is 1. Okay. So EMF equals negative 100, so we're just subbing in n equals 100. The change in magnetic flux, area doesn't change, so we can factor that out. B final minus B initial, divided by the rate of change, the change in time, which was given as 0.02. Area of a loop is just pi r squared. R in this case is 0.014, and we square that. Find the difference. of this. So 0.03 minus 0.51 is just negative 0.48. We divide that by 0.02. The signs don't matter because we're after magnitude, but you know, either way, it doesn't matter too much. Now we should get the magnitude after subbing the values in. Okay, I will disable this because calculator is not easily visible. Actually, wait. Yeah. I'll angle it up, actually. Yeah. Maybe that's a smart idea. Okay, so 100 times pi times 0.014 squared times 0.48 and then divide by 0.02. So we get an answer of 1.48 volts. Now that should be our answer. 148. Yeah, they just rounded it to 2 significant figures. Oh my days, wait a minute. No. No, no. Wait, what? Hopefully that doesn't matter. Wait, that just reminds me, in chemistry, I didn't really care about significant figures. They didn't ask, like, specific significant figures. 1.5. Okay, I mean, I'm still right. Like, you know, I'm assuming they allow different significant figures. I'm assuming, hopefully. Because then again, I was thinking, oh, they're all given in two significant figures, but this one isn't, so who knows? Calculate the strength of the star's gravitational field experienced by the spaceship. So we're dealing with gravitational field. Okay, so lowercase g. Calculate the strength of the stars. So we just, for this part, we ignore the planet. So the mass of the star is 1.9 times 10 to the 30. The radius from the spaceship to the star is not 2.4. It's not just 2.4. 2.4 plus 3.6 times 10 to the 11. So this adds up to 6 times 10 to the 11 because they have same scientific notation. So you can like factor it out, and then you just add these, which gives 6. That's 6 times 10 to the 11 meters. Okay. And then what do? We use our formula. So lowercase g, since we're dealing with gravitational field strength, right? Big G r squared. That's on the formula sheet, so don't worry too much if you don't remember that. So we're multiplying 6.67 times 10 to the negative 11 with 1.9 times 10 to the 30 divided by r squared. So we need to square the entire thing. I apologize if you can hear like rain and thunder outside. Right now, there's like a storm. I don't know. Okay, we just put that in our calculator. 6.67 times 10 to the negative 11. That's 1.9 times 10 to the 30. This is divided by 6 times 10 to the 11. And you... Okay, maybe I will disable this just for these purposes. Yeah, it's much clearer. And yeah. Okay, so it's 3.52 times 10 to the negative 4. Meters per second squared. Okay. So now what do? We see if we're correct. That's what we do. Yeah. Okay. We are correct. At least I think, because the significant figures are different, but I think we're correct. See, in this question, they do actually have two significant figures. See, that's what worries me. I don't know. I don't know. Okay, an observer on the planet measures. I mean, to be honest, if they penalize you for wrong significant figures, I feel like that's just dumb. Like, why? Like, what? You know? An observer on the planet measures the spaceship to be traveling directly towards the star at a speed of 1.9 times 10 to the 8. Calculate the distance between the spaceship and the star from the perspective of an astronaut. Okay, so this is actually not relevant at all to gravitational, like, gravity and stuff. This is special relativity. That's interesting. Okay. I'll just write down the velocity. 1.9 times 10 to the 8. See, 10 to the 8 means it's quite, yeah, it's like relativistic speed, like a lot. That's like, what, 60% the speed of light? Yeah, wow. Close enough, close enough. It's not exact. Okay. Calculate the distance between the spaceship and the star from the perspective of an astronaut on the spaceship. So we're dealing with length contraction. So I've written the value down here. Okay, so I'll go to the next page. You know what? So the velocity was 1.9 times 10 to the 8 meters per second. Okay. Dilated length equals contracted length. I mean, yeah, contracted length equals through length. And then, is this correct? I think so. See, instead of being, a bit doubtful like me, just, be smart and check the formula sheet. Do not, like, waste time just thinking when you have access to a formula sheet in the exam. The distance we calculated 6 times 10 to the 11, right? That was the radius. Yep, that was the radius from the spaceship, or the distance from the spaceship to the star. But that was the dilated length. In terms of relative to the observer on the spaceship. This seems wrong. Yeah, okay. Let's check our formula sheet. It isn't. Okay, well, that's because I'm applying the question. That's the true length. This is the true length. So what I wrote here is basically correct. What I was going to write was square root, but this is actually the correct thing. So in this case, the dilated length, so just L, would be the length that is being measured by the observer on the spaceship. True length is when it's measured in an inertial frame of reference to that distance. Since, you know, if you're at rest, that's at rest relative to you, you can get an accurate measurement. In this case, no, they're moving at 1.9 times 10 to the 8, and then we divide that by 3.3 times 10 to the 8, and we square it. These cancel out. We can just put that in a calculator, call it a day. Okay. 6 times 10 to the 11 multiplied by the square root of 1 minus, and then we put brackets around it, 1.9 divided by 3, and then we square that. Okay, obviously the distance is going to be large. Put it to two significant figures, whatever. Okay, 3, 6, 9, 11. 4.6 times 10 to the 11 meters. Let's see if we're correct. 4.6 times 10 to the 11. So in this case, we did correct rounding, or correct, yeah, rounding to two significant figures. Yeah. Not sure if you'll be penalized. I don't know. Let's just keep going. Let's not think about that. A student conducted an experiment to address the following research question. What is the relationship between the angle of inclination and the acceleration from rest down a 2.4 meter slope of a 0.05 kilogram object? Data from the experiment was processed to produce the following graph. So we have this graph. Okay. Determine the magnitude of the frictional force acting on the object when the angle of inclination is 45 degrees. Use the graph to show you're working. So the angle, okay, well, x represents sine theta. What's sine of 45 degrees as a decimal? It's 0.71. Okay, that's rounded to two significant figures. 0.71 is like here. So what's that? 5.9 approximately acceleration. So what you'd write is like, oh, sine of 45 degrees equals 0.71 roughly. So we'd use like this symbol. And then what you do is on the graph, you know, A is roughly like 5.9, right? So if we go over here, it's like roughly 5.9 meters per second squared at sine theta equals 0.71. Okay. F net equals, so the net force equals mass times the net acceleration. We are given in the question what the mass of the object is. It's 0.05. Multiply that by the acceleration we got, which is 5.9. We get an answer 0.295 newtons. And of course, this is down the slope. So first, let's try and draw like, well, not try and, but actually draw a free body diagram of the object. We can ignore the vertical components. We're just focusing on the horizontal components, or you could say parallel. So this is the force due to the weight. So then we resolve this into its parallel component. So this part would actually be sine 45 degrees, because we know that due to the complementary angles, 45 degrees here goes to 45 degrees at this angle in the triangle. And then since the hypotenuse is W, or the weight, and we're dealing with the opposite side for the parallel component, we're dealing with sine. And then we rearrange, right? So sine of 45 degrees would equal opposite, which is the parallel component. So let's say Wx over hypotenuse, and then we rearrange to get this. Okay. This is acting downwards. So W sine 45 degrees is acting downwards, and then we subtract the force due to friction. I think the question is after the frictional force. It says magnitude. So that's why I did minus, because then it will give me a positive answer. So this is net force, basically. Okay. Weight is mg. And then sine of 45 degrees is just square root 2 over 2. And then we sub in 0.295 for the net force. Okay, and m is 0.05. We multiply by 9.8. And then multiply by square root 2 over 2. Minus 0.295. And then add the frictional force to isolate it. Then what we do sub those values in. 0.05 times 9.8 times square root 2. This is all divided by 2, and then we minus 0.295 to get a frictional force of 0.05. Okay. So rather than, instead of writing 0.05, I'm going to write 0.051 in case that they're asking for two significant figures. Okay, so they got a slightly different acceleration value. But inherently, it's the same. Okay. Yeah. So I would accept that. Calculate the final velocity of the object when the angle of inclination is 45 degrees. Show your working. We're given that the length of the slope is 2.4. We know also, what else do we know actually? It accelerates from rest. Okay, if it's at rest initially, that means u equals 0. Okay. We can use v squared equals u squared plus 2as. That's on the formula sheet. We're trying to find the final velocity. We're trying to find v. V equals plus minus square root, in this case, u squared is just 0 squared, so we don't care about it. We know what the acceleration is. It's like 5.9, right? At 45 degrees incline. And then S is just 2.4. We sub those values in. What do we get? It says final velocity. We ignore the plus minus, and instead what we write, so we sub in the values, 2 times 5.9 times 2.4. We get an answer of 5.3 meters per second down the slope. So that's the direction, and the speed is 5.3. Calculate the final velocity, yep. We use the same formula, 5.3. Okay. They didn't specify down the slope, but alright. Oh, wait, because... Okay, never mind. Yeah, it doesn't give any space for you to write that. Explain how a satellite can be accelerating, yet maintain a constant speed in a circular orbit around a planet. This is, in line with circular motion, right? So what you'd have is just... I can use this again. Okay. We can use this to demonstrate. I don't know if it's visible. Yeah, it's not visible. I'll try and use the other screen. So the constant speed is an interesting part about centripetal force. So if I spin this, I'll decrease the radius so it's actually visible. Yeah, so if I spin this, right, I can kind of maintain the speed. However, even if I maintain it, that means I'm applying an acceleration constantly to maintain it. So what this question is asking for is, how come, although it's accelerating, how come it can maintain a constant speed? And fair enough. If an object is accelerating, doesn't that mean there's a rate of change in velocity? Well, I just kind of implied why there's a constant speed. Velocity isn't just speed, it has direction. That's one part of it. Let's draw a circle, right? So in this case, this is the center of motion. Centripetal acceleration is always acting radially inwards towards to the trajectory, right? So this is the centripetal acceleration. Velocity could be going this way, could be going this way, right? It's tangential, so we don't really know. However, we know that the speed is the same, right? It's going to keep going around at the same speed. Acceleration doesn't contribute to a change in velocity in this case. I mean, a change in speed in this case, because it's acting perpendicular, right? If velocity is going this way, but you're applying acceleration that way, like, for example, in a good, something that relates to this, independence between, like, horizontal and vertical vector components, is projectile motion. We know we can resolve projectile motion into its horizontal, so it's x, and its vertical, its y components. So they're independent of each other, right? We usually assume, in our projectile motion questions that, air resistance is negligible or just non-existent. However, there's acceleration due to gravity that acts downwards, but that doesn't affect the horizontal velocity in any way. Same thing with this. This is acting perpendicular, so it doesn't contribute to how quickly it goes in this direction. All it's doing is changing the direction. And you might be thinking, what happens when it's, over here and now the tangent is a bit different? Good question. Well, since the acceleration is always acting, radially inwards, it will never not be perpendicular. It will always be perpendicular to the velocity, and hence there's no change in speed. Okay, that seems like a good explanation, but I definitely think I wouldn't get 4 marks for that. Yeah. Okay, let's think about it. So a constant force, centripetal force, is required to maintain the orbit, right? But because it's acting radially inwards, the acceleration doesn't contribute to a change in speed because it doesn't act, it doesn't have a parallel component to the velocity. It doesn't have a parallel component to the tangential velocity. Rather, it's all perpendicular. So it only results in a change in direction, which then contributes to the uniform circular motion. Let's see. Inertia. What? Okay. Really? We have to say inertial. Wow. Identifies that planet provides centripetal force. Explains that changing direction means change in velocity, which is acceleration. Describes inertia of satellite. Oh my days. Okay. 3 marks, I'd say. I did not state inertia, but overall, decent explanation. Okay, but inertia, yeah, I didn't think it would be relevant, to be honest, for that. Explain the significance of the threshold frequency when incident light with a range of frequencies shines on a metal. Okay, a range of frequencies. Immediately, I'm thinking we need to say what happens when the incident light has a frequency below the threshold frequency, and then what happens when it's above the threshold frequency. Yeah. Okay. Well, the threshold frequency is the frequency required by incident photons to actually cause the photoelectric effect, to actually allow electrons to ionize and escape from the metal surface due to them being excited by the absorption of those photons. When incident light has a frequency lower than the threshold frequency, the incident photons have insufficient energy to allow the electrons to ionize and escape the surface of the metal. So nothing really happens, right? No voltage is produced. However, when the incident light has a frequency above the threshold frequency, they can become ionized because they have sufficient energy to ionize and increase in transition state once absorption occurs, and hence causes a current to take place. Like electrons can freely escape the metal and cause there to be kinetic energy. Yeah, I don't know. Okay. Minimum frequency of a photon required to eject a photoelectron. I basically said that. In this case, photons with frequencies equal to or greater than the threshold frequency will eject photoelectrons from the surface of the metal, while photons with low frequency will scatter off the metal surface. Okay, again, I don't know. I basically said the first two. Last one, like I understand, like oh, if you don't have enough energy, you'll just reflect off. I guess a lot of it will reflect off, but at the same time, they can still be absorbed. Like electrons can still absorb photons. It's just that, I'll give myself four. Yeah, they scatter off because you need. So, for example, like if you think about Bohr's model of the atom, you know, electrons only absorb photons with specific frequencies or wavelengths. Otherwise, they're just like reflected. Yeah. Okay. It's not looking too good. Photoelectric effect experiment was set up with a variable voltage between the collector and emitter, a resistor, and an ammeter. There was no current detected when the light was off. The potential difference required to reduce the current to zero was measured for differing wavelengths. Determine the potential difference required to reduce the current to zero when light with a wavelength of 125 nanometers is shone on the emitter. Show your working and refer to the graph. Okay, this is pretty simple. 125 nanometers. How much is that? Well, 1 over lambda is the x-axis. So in this case, we want 25 nanometers, which is, 125 nanometers. So it's 125 times 10 to the negative 9. I accidentally wrote 19. What value is that? It's 8 million, so 8 times 10 to the 6, I think. Yeah. So then we go back to the question. Um, in terms of 10 times, um, that in terms of times 10 to the 7. So in this case, I'd have it at 0.8 times 10 to the 7, because that would be 8 times 10 to the 6. Okay, so it would be at this point, and the potential difference is negative 4.8. Negative 4.8, yeah. Part B, use the graph to determine the work function of the emitter in electron volts. Okay. Pretty big question, pretty big part of the question, but it should be pretty simple. Okay, and I'm not being overconfident. Don't let it overwhelm you. Ensure that every question you at least try before you get scared. Okay, because that's very crucial. We know that potential difference, we can use this, right? We know the charge, it's an electron. So it's 1.6 times 10 to the negative 19. The change in energy, guess what? Kinetic energy. photons have kinetic energy, which is energy, you know? Something to think about. But first, we're going to write kinetic energy max, and the maximum kinetic energy equals hf minus the work function. We're trying to find out the work function. Okay, so work function of the emitter in electron volts, and then here's the graph. Okay. So first, what does the gradient represent? Yeah, what does the gradient represent? It's V over 1 over lambda. Okay. That's very weird. That's very weird. Can we use this and somehow rearrange to get something like this? It'll be a bit tough, but hopefully we should be able to do it. Okay, let's think about it. What's the change in energy? Final minus initial, right? Final is 0 because it's how they said it's the amount of it's the potential difference required to stop the electron flow. So, after you apply the potential difference, it's going to be 0. So it's going to be minus U, which is the kinetic energy max, over Q. So that's V, right? And then we can sub the values in. So W minus HF over Q equals V. So since we distributed the negative, it makes the work function positive and then this negative. Okay. I think this works. W over Q minus HF over Q. So I just distributed the denominators, right? You can do that. Okay, we're not breaking physics here. Okay, we can do that. We can use the wave equation. So in this case, we're talking about photons, right? The frequency of the photon. So we can use c equals f lambda. Usually it's v equals f lambda, but in this case, the speed of light, is c. We rearrange for f, right? Pretty simple, and we sub that in. So v equals negative h c over lambda times q, so q lambda. And then we add w over q. Okay? Okay, this makes sense. It looks promising because we have a negative gradient. Oh, wait, no. We've ran into an issue. We'll continue. If it's the wrong way around, we'll just invert the negative. Yeah, whatever. Okay. So then V equals negative HC over Q multiplied by 1 over lambda plus WQ. Okay, we have a linear equation. V is Y, 1 over lambda is X. So therefore, gradient equals negative HCQ. Okay. Yeah. Seems correct, except No, no, no. We'll continue. We'll continue. Let's not make assumptions and think, oh, wait a minute. Hold on. Like, work function isn't even in here. We can calculate this and then sub in a value for the work function. You know? Okay. What is the gradient? Okay, let's use the gradient. Find a point. Find a very useful point. Okay, something very easy. Um, there's one point at the top, so the second highest point. Um, I'll mark it down. So the x value is 0.5 times 10 to the 7, approximately. And then the y value is just -1, approximately. Another point. Let's find something suitable. Okay, the one here, yeah, second lowest point. Okay, 1 times 10 to the 7, and then it's approximately -7.3. Something like that. Okay. So now we have this. So we just do rise over run. So we can get this minus -1 over, I don't know why I put brackets around the entire thing. 1 times 10 to the 7 minus 0.5 times 10 to the 7. We don't really need to use a calculator to simplify. 1 minus this is -6 point that. And then we can ignore the scientific notation. So all we get is 0.5 times 10 to the 7. Okay. Oh, no, no, no. This is completely fine. Since it's a negative gradient, the negatives cancel. Okay. Yeah. So then it becomes 6.3 times 5 times 10 to the 6. So what I did is I just didn't like it being in a decimal, you know? So I multiplied 0.5 by 10 and then just decreased the exponent by 1, you know? This becomes positive because we're cancelling out the negatives. Oh, no, no. That doesn't matter, actually. Okay, so this equals negative hc over q. So we then sub it back into this. B equals negative 6.3, 5 times 10 to the 6, 1 lambda plus wq. So the y-intercept should equal w over q. Sub any point, we'll just sub this value, yeah. 10 to the 7 minus 7.3. Okay, what can we do? We go this 1.63. I mean, what numbers am I saying? Like, I'm saying random numbers. Okay, times 10 to the 7 because 1 doesn't affect it, right? Okay, plus w over q. This cancels with this, leaving us with 10, so then it goes to negative 63. Okay. So then we have 63 over 5 minus 7.3 equals w over q. Okay. It's going to be a negative value. So we're just going to turn it positive. Yeah. Yeah, I'm not sure what went wrong in terms of like the signs, but yeah, okay, it's going to be a negative value anyway. Um, we multiply. Okay, first let's actually get that. 63 divided by 5 minus 7.3, 5.3. Then we times that by q, which is 1.6 times 10 to the negative 19. That's the work function. Yeah, I'm not sure what happened. Yeah, not too sure. Okay. Yeah, I don't know. I don't really know. Um, anyways, let's actually calculate it. So we times the answer by the charge. But then we also divide it. Oh, what? That's dumb. Okay, so it's 5.3 in electron volts. The reason why I divided it again by 1.6 times 10 to the negative 19 was because it's asking for it in electron volts. Okay, they got 5.1. I mean, there's gonna be rounding errors based on um what values you chose. So yeah, that's something. For stopping voltage, oh what? EK is not negative. Okay, whatever. Um, yeah. Wait, what? They just subbed in 1 point. Are you serious? Are you serious? What? I thought you had to interpret the gradient and do all that stuff, but you just sub in a point. Hmm. Don't know how I feel about that. Anyways, the experiment was changed so that variable voltage was removed and the light with a frequency above the threshold frequency was shining on the emitter. Predict the effect of increasing intensity from the light source on the current in the circuit. Explain your reasoning. Well, okay, so the light has a frequency above the threshold frequency. It's not variable, which means each photon is going to ionize. It's going to be capable of ionizing each electron and ejecting photoelectrons from the metal, right? So we're going to have current in the circuit, right? So in this circuit, there's going to be current flowing between the emitter and collector. The electrons are going to be able to be ejected. They're going to eject as photoelectrons, and then they're going to pass through the collector, go through the circuit. If you increase intensity, you're increasing the amount of photons present. If you're increasing the amount of photons present, that's like directly proportional to the current. So since you're increasing the amount of photons, and each photon is capable of ejecting the electrons as photoelectrons, you're going to be creating more current. That's all I can say, to be honest. I don't know. I'm definitely missing something, but since frequency is above threshold frequency, increasing intensity will produce more photons. Will increase the likelihood of photoelectrons being knocked off. I mean, I basically said that. Okay, I'll accept that. Contrast baryons and mesons in terms of composition. Baryons, okay, this is pretty easy, 4 marks. Baryons, baryons and mesons. I know this isn't compared, but just for your information, baryons and mesons are types of hadrons, right? Which are quark composites. Baryons are, you know, quark composites that have 3 quarks. Mesons have a Quark and anti-quark pair. Okay, yeah. Contrast quarks and leptons. Um, Quarks can experience the strong nuclear force. Leptons can't. Pretty simple. Three quarks, whereas mesons. Baryons are composed of three quarks, whereas mesons are composed of one quark, one anti-quark. Yep. I mean, I just said like, okay, see, like I was trying to keep my answers succinct, but okay, fair enough. Quarks experience all the fundamental forces. So strong, all four fundamental forces: so strong nuclear, weak nuclear, electromagnetic, and gravitational. Leptons experience only the weak nuclear force, gravitational force, and electromagnetic force if they have a charge. Because that's important to note because some leptons don't have a charge, and that's the neutrinos, right? So electron neutrino, tau neutrino, muon neutrino, they have a charge of 0, while the electron and muon and tau have -1. So that's pretty important. See, I'm aware of this, but I didn't say it. So it doesn't matter, like if I'm aware of it, I didn't say it. A U-shaped magnet, like for example, if I'm thinking of helping someone on the street, like someone's being attacked, doesn't matter. I like, oh, that's not going to change anything. That's not going to change the outcome. The person's still getting attacked, and currently I'm not doing anything. So that's all. You know, if you were an outside observer, that's all you'd see. No one's helping the person. Who cares if you're thinking about helping? No, it's your actions that matter. A U-shaped magnet was placed on a digital scale. Okay, nice, good to know. A current carrying wire was connected to a variable power supply and passed through the space between the poles of the magnet. The length of wire within the magnetic field was 0.08 meters, and the wire did not touch the magnet. Okay. 90 degrees. Sketch the magnetic field between the north and south poles of the magnet when there is no current in the wire. I mean, let's draw the magnet. It's like something like this, right? And then pole of the magnet is on the left side and it's on the right side. So the magnetic field lines are just going left to right. Is it? Is it? Hold on. No, I think that's true. Wait. See, this is why I need to revise electromagnetism. Okay, never mind. Okay, never mind. I guess I was overthinking. Um, the power supply was switched on. Readings from the digital scale were recorded while the current in the wire was varied to produce the graph shown. So as current increases, the mass increases, which means force is acting downwards on the magnet. Identify the mass of the magnet. 1 mark. Draw the gradient. Find where current is 0, which is the y-axis, y-intercept. It's going to be like 0.96, right? Come on. Come on, this is too easy. This is too easy. Oh, I forgot to change the screen. I apologize. There's going to be a line kind of going like that. So you can see, based on the line of best fit, if you were to draw a line, it would be around 0.96 kilograms, which I believe is the answer. Yeah, y-intercept 0.96. Okay. And then part C is where the majority of the marks in this last question are. Determine the strength of the magnetic field produced by the magnet. Show you working. Okay. The length of wire, pretty important, 0.8, 0.08. So let's write that down somewhere. It's in meters, which is, thank you. I'm grateful for that. We're given that it's 90 degrees. The wire is perpendicular to the magnetic field. I believe we're using force equals BIL sine theta. And sine theta is 1 in this case because sine of 90 degrees is 1. I think that's the formula we're using. So we, in this case, would use the gradient on the graph. That does become useful in this case. Mass and current. Okay. So we're combining the force with force due to gravity. No, we aren't. No, we aren't. Wait. The gradient, um, hmm. No, we do, right? F equals ma to convert the mass into a force, right? Okay. Gravity equals mg, right? In this case, we know m. Yeah. So Fg over G equals m. I think this is what you're meant to do. I believe so. Might be wrong, but yeah. Okay. So what was the question asking for again? The strength of the magnetic field. So we're after B. Okay. I think this is correct. So then what we do is the gradient is m over I, right? So this equals the gradient. And what is the gradient? Well, in this case, it's rise over run, so we can use point on the graph. Let's choose. This one's a good point, where my cursor's on. Okay, first we'll choose the one at the very top right. So I think that's like 76, 77, 78, 78.5, 0.9785. I need to charge the laptop. Okay. So 0.9785, I've written that. And then the other point I was talking about was 0.971. This, the first point was at 5, and the second point was at 3. Okay, so what's the value? Well, guess what? We put it in our calculator to determine the value. 0.9785 minus 0.7971. That gets that. Divided by 2 because that's the difference. We get 0.0375. That's the gradient. However, it's a bit misleading right now because we need to convert this equals mi, right? Okay, we'll go to the next page. But remember, mi equals this, and that's from Newton's second law. But for gravity, because in this case, the mass due to gravity isn't like the scale readings represent the mass, but then also the increase in mass is due to the force due to gravity, but it's actually also technically the force acting on the wire from the magnetic field. So then it's this equals 0.00 whatever I wrote, yeah, 375. Okay. So this goes down, so then we're multiplying it. Force due to gravity in this case is actually the force acting on the wire due to the magnetic field. It's the answer by 9.8, which we get 0.03675. I could be doing this very incorrectly, by the way, so just be aware. F equals BIL. Wait a minute. Oh, wait, no. Oh, I was about to say, wait, like, something's up. Not necessarily, no. We know, so if we rearrange, we get this, so we can just sub this value in, and then we divide it by the length, which was given, 0.08. That should be our force, our magnetic field strength. I don't know if, like, my 0.459375 Teslas, but, we have like the notation and like 3 significant figures, so we'll use the 3 significant figures. 0.4. No, we'll use 2 Teslas. 0.46. Actually, no. 3 significant figures. It's probably wrong anyway. Don't know why I'm doing too much. Okay, so yeah, I get 2 marks at least. Hey. Okay. Force due to magnetic field equals the force from the scale reading minus the weight of the magnet. Yeah, that's basically what I was trying to say. Yeah. Okay, so rather than using the gradient, they just sub in a value. Okay. Subbing in a value is much quicker. You know, saves you a lot of time. Yeah. Scale reading minus weight of the magnet. Yep. Okay, but overall, essentially the same value. So I would accept that. Yeah, it's essentially the same thing. But yeah, I think this one, the notation or like how they handle the difference in force and what the force is attributed to, it's handled much better. So this sample response makes much more sense than whatever I did, right? This is this is a monstrosity. Like it doesn't really make sense because, you know, I'm saying that force due to gravity is responsible for the change in mass. What? You know? Doesn't yeah, doesn't really make sense. Whereas this makes absolute sense. This is correct. This is definitely correct. Um yeah, so this is something you should follow more if there's a question similar to this, which I highly doubt. But yeah, it's pretty good. I still basically got the value, except there's a bit of a difference because I calculated the gradient and I used different values. But yeah, hope that helps. And yeah, good luck with physics.